equal to 0. That's a non-trivial 0 in the span, right? Okay, so these are no longer linearly independent, which means if we multiplied this by, what was that? Minus 2, 1, this would be 0.
Is minus 2, 1 just a thing that you chose just at random, or?
I chose it because it's the linear combination of these two columns that gives me 0.
Okay, okay.
So minus 2 times A1 plus A2. That's minus 2 times this column, 1 times this column, right? And that's equal to 0 because this will be negative 2 plus 2, this will be negative 4 plus 4.
So if this is the case, is it always going to be that like A2 is some multiple of A1?
No.
So like 3 and 6, or is it?
I'm glad you asked that because this could possibly be a misleading. It's only the case when there are two vectors.
Okay.
So if there are two vectors, the only way they can be linearly dependent, which means we can do something like this, we can find a non-trivial 0, is if one of them is a multiple of the other. Now if there's more than one, I'm going to give you an example in 3 by 3. So 1, 2, 3, 4, 5, 6, and now I have to think for a second, minus 5, minus 7, minus 9. Okay.
Yeah,
None of
I've
these
done
is
that
a
all the
none of
time.
these is a scalar multiple of the other, right? And these are not linearly dependent. I mean, these are not linearly independent. They are linearly dependent because I can find a linear combination of them. This one plus this one plus this one equals 0. So it's definitely not the case. It's bigger than just scalar multiples. If I had 1, 2, 3, 2, 4, 6, and then who cares what's here, also linearly dependent. So if you find that one column is a multiple of the other, you instantly know that they're linearly dependent because what's something that gives me 0? Minus 2, 1, and then 0. Not anything. No matter what this is, I zero this one out, and then I'll say this minus 2 times this, and that's 0.
And if there are set values in the third column, does that make a difference?
No, right, because I'm multiplying by 0, it doesn't matter. In order for it to be a non-trivial linear combination, just some of the weights have to be non-zero. So I just picked these two to be non-zero. For example, I could have like a million columns after this. I just zero them all out. I know instantly that they're linearly dependent.
So is it that if any two columns are multiples, scalar multiples, then same concept applies, or dependent?
Yeah. So, but that's just one narrow case.
But that's still there are more cases.
There are more cases like the ones I showed before. So let's 1, 2, 3, and what did I have before? Well, let's just do 0, 0. Okay. Now, any linear combination of these two vectors, if I want it to be linearly independent, I have to exclude all those things from here. So, for example, I put 1, 3, 3 here, or let's do 1 here, 3 here, and 60. Is it obvious that this thing is a linear combination of those two?
Not to me.
Okay, so this is A1, A2. So A1 plus, so A1 plus any multiple of A2 is going to be 1 in this entry. For this entry, 3 times any multiple of A2 will be 3. So I'm totally free to pick this multiple to be whatever I want. So I pick it to be 58 A2. And now suddenly I've got this thing right here. So to get a non-trivial 0, just subtract away A3, and all of a sudden I've got a linear combination of the columns is equal to 0. So yeah, the concept of linear independence is like multiples, but it's bigger. If we were only looking in 1 dimension or 2 dimensions, it would be the same thing. But in higher number of dimensions, it's a bigger concept. So that's the one-to-one and onto. Hope that's clear. Yes.
Distilling it down simply, we could say that it's onto certainly if there are no rows of all zeros or something like that, right? Would that be a rule we could, like a blanket rule we could put for that? Because that's the same as saying the system's consistent, right? Which is.
That's the same as saying it's consistent.
And that's how we say that.
Couldn't you say it's onto if you have more
Yeah, you're right.
rows than you do columns?
You could say say that again?
If you have more rows than you do columns, wouldn't that make it onto?
Well, this is a case where we have more rows than columns, and it's not onto. It will never be onto if you have more rows than columns, because we will always be going from a smaller dimensional space into a larger dimensional space. Now, if we go the other way around, we still can't say that.
Oh, yeah, I see, I said it backwards, yeah.
Yeah. So,
See, the opposite of what I said, would that work?
also not.
Oh, okay.
So we have to see. One of the interesting things about linear algebra in vector spaces is that we can figure out whether or not it's one-to-one and onto strictly based on the dimension of the output. So in this case, we had 3 independent vectors, so the dimension of our output was 3, which means that this 3-dimensional input goes to a 3-dimensional output inside here. And we could conclude just from that it's one-to-one. We did it in terms of saying that there's no non-trivial zeros, which is the same thing as saying the columns are linearly independent, right? And that leads us, because of linearity, to this kind of consideration, which is the definition of one-to-one. But because we know all these things are interconnected, like you were saying before, all of these similar ways of saying the same thing, different concepts, but we find that they're connected to each other. That's one of the things about linear algebra, is everything kind of simplifies down to a bunch of things being the same. This is one of those cases. The dimension, what the dimension of the output is, will tell you everything you need to know about one-to-one and onto. So, if you have a transformation from Rn to Rm, then it can only be one-to-one if n is less than or equal, well, how should I put this? And we should also say what the range of t is. So the range of t, as long as it's a linear transformation, this will also be some rk, let's say. So rk, and this sits inside our codomain, Rm. Right? This is going to be the span of the columns. Right?
So you said the transformation tells you everything you need to know about onto and one-to-one?
The dimensions that we get from it.
Okay, the dimensions like, so N and M tell you everything you need to know?
So the range, if it's onto, this means K equals N. So the dimension of the range is the same as the dimension of the codomain. What we have here is a K-dimensional space. So if this is a plane, then it's R2, right? So in order for that plane to hit everything in this space, in the codomain, that codomain better be R2 as well, right? It can't be R1, well, I better clarify that. It's gotta be at least as big. Because if this is R1, then, well, we got a weird situation where we said the span is bigger than this.
So if you just say it's
Really happy
onto,
with it.
so if you have more inputs than you do, like spaces in your codomain, then you'll at least be onto, like you'll fill up that space completely, and you'll have extras that might drop off from your input, and that's okay.
Well, here's the thing. Let's say we had this vector, or this matrix, 1, 2, 3, 4, 5, 6, 5, 7, 9. The example that we had earlier. So this one would be a map. It takes a three-dimensional input, right? I want to make sure I'm not going through these things so quickly that people are getting frustrated. Everybody's following along with me?
One question, you said the dimensions of what tell you everything you need to know? I think, all right, I was trying to think of.
I'm getting to that.
Yeah, okay.
So this is, the inputs will for this will be three-dimensional, right? And the outputs will be three-dimensional. Right? But this is not onto, right? Even if let's see. Even if I made this, well, we saw the example with when I had more rows and columns. Let's make more columns than rows. Let's do 6, 9, 12. So there's only two linearly independent columns in this. These two are linearly independent. But this is a combination of these two, and this is a combination of these two. This one is this one plus this one. This one is this one plus 2 times this one. Okay? So the span of the output, is the span of just these two vectors. So if I call this T, then the range of T is just, I shouldn't say it's R2. That's actually kind of bad. Let me change the way I talk about this. I should say the range of T is equal to the span of A1 up to A2. That's a better way to put this. So the output of this transformation is just the span of these two vectors, because these two are already in the span. They don't actually add anything else. They're not linearly independent. So this is a k-dimensional subspace of this. I'm using terminology that I probably shouldn't get to yet. Anyway, what we know is that
did you say A1, A2, or A1, AK?
A1 up to AK.
Okay.
So I'm just speaking in generality, this is the minimum number of vectors that's necessary to span the range.
Okay.
So when we talk about is this onto, then this K right here has to be equal to M. And in terms of pivots, that means that we have as many pivots as we have columns. Oh, for onto, yeah. As many pivots as we have rows. Right. Yeah, I'm looking at this example, we can't have that because we have more rows than we have columns.
So that be K equals N? Right? No, never mind, I'm sorry.
Yeah, N is the number of rows.
Yeah, I'm sorry.
Okay, and then, we have to have as many, all of these vectors have to be linearly independent in order for this to be one-to-one, right? And so, in that case, K has to be equal to N, and that gives us. And this corresponds to there being a pivot in every column.
So if a matrix is gonna be one-to-one and onto, by that, it has to be like an n by n matrix, right?
Yeah, exactly. Yeah, that's a good observation. The only way for it to be one-to-one and onto, or as serious mathematicians like to say, bijective, then it has to be n by n, it has to be square, and in fact it has to be invertible, which means, well, it's the same thing as saying that it's square and all of its columns are independent. Okay, so does this answer your question?
I don't even remember my question, but there's nothing that I
Well, I
had a
don't
question
remember
about
either,
at this
so-
point, so I guess it did, so otherwise I'd still be wondering.
Okay. Good. Yeah, we figure out how many vectors it takes to span the output. That's what this row reduction algorithm does. It gets the matrix into a reduced form, which shows us how many independent columns there are, right? There's one for each pivot. And so if we have as many pivots as we have rows, that means our output is the same dimension as the span of the columns.
Okay, so I think I remember now. So the dimensions of, so basically the values of n and m tell you everything you need to know about 1 and 1 and 1, 2.
No.
Okay.
You also have to know if the columns are independent. How many of the columns are independent?
Okay. Gotcha.
Does this answer your question?
Be better about it.
Okay.
Yeah, thank you.
And RK is going to be, never mind.
So
K is how many columns are in it. That's all.
K is how many linearly independent columns we have. Are we already out of time?
Yeah, sorry, I talked a lot.
I feel like it is, well, okay, so this is a review day. I will stay here as long as you have questions. Right? You're free to leave, well, you're always free to leave, you didn't even have to come today if you didn't want to. It was Wednesday, just a reminder. But feel free to just keep asking questions. This is your last chance.
recording?
Yeah, I'll keep recording.
Okay, thank you. Yeah, I've got another class.
Um,
And it's a lab, I can't skip a lab.
I have one of those, I'm interested in that question too.
This is not the line. I tried to figure out what it does, and my eyes started to cross. That's my test.
Well, actually, just today I found out it has a matrix function.
Oh, so
section
that's-
on here, at least one minute.
I've never played around with it too much.
Yeah, I just found out, like, homework would have been easier.
Oh, is that TI 34 or whatever it is?
Yeah.
Yeah.
That's pretty cool that it's solar powered though.
Probably if it's got only room to display just numbers and no like symbols or anything, I bet it's fine. Because you can't do matrix functions on anything that only displays numbers, because you have no idea what you're inputting with that.
I'm not gonna lie, I have no idea what this window's for, because like,
That's the solar.
is it actually?
Yeah.
So, that's crazy.
I remember when I was a kid, I covered it for a while.
Interestingly, in renewable energy with Dr. Doloff right now, we've covered kind of the solar spectrum. And solar panels can absorb a lot of, actually the visible light spectrum is like mostly what they can absorb from what I can tell. So, and maybe like,
I've got one more quick question for you.
point is,
Can I ask one more question?
the
Yeah,
fluorescent lights.
you can ask 100 more questions.
I've asked coming up, also, I've always said on this, but, again, example on the book, this is number 3 right here.
Interesting.
It actually asks about transportation stuff, and if it's unique or not, that's a particular question. Number 3. I'm doing some work, but I wanted to ask you a particular question. I reduced everything down, I got the right answer. Can I say it's unique because of this last line in particular saying, I've got one answer for X3, which is gonna dictate my answers for X2 and 1? And that's a unique particular solution?
Yeah, that's totally valid reasoning. What we had been doing with the row reduction is actually using this last row to eliminate these two right here,
Mm-hmm.
and that gives you an exact answer for X1, X2, and X3. So there's in fact no room for other possibilities.
I think it defines uniqueness in the book as far as row reduction goes, if you don't mind.
Yeah.
I was looking at it the other day, it says, when you row reduce it says, if it looks like this, then you know it's unique. If it
Certain
doesn't-
form.
Yeah,
It is exactly what we were saying before, because from this you have a pivot in each column,
yeah.
and so that means the columns are linearly independent. So it's 1 to 1, so all of them are unique.
So it says, a linear system is consistent if and only if the rightmost column is an augmented matrix, is not a pivot column, so like what it's equal to. And then if it's consistent, then you ask, if it's consistent, a unique solution, it has no free variables, which we were just saying. And if it has a free variable, it's not unique. Yeah, because then,
Yeah, that's exactly what it is.
And then consistency is that what it,
and then I think it says.
what does that mean?
Yeah, so
I'm looking at
consistency
that
means
yesterday.
there's no row of the form zeros equal B, so you can't have 0 equals 2, because that doesn't make any sense.
Yeah, so that's,
So like, if I zero out an entire row, that means it's not a consistent
well,
thing?
as long as you get zeros all the way over, if you have to augment it, it's
I
not
have
zero.
one financial column, for example,
Yeah.
that's not consistent, that cannot happen in column.
Yeah, you can't say like 0 x.
It's just like right here, where I noted this, I did this problem, I got 0, 0, 0, 3, I say that can't happen.
That's inconsistent. Yeah,
Okay.
exactly.
Okay, that makes sense.
That means there's no solution. There's nothing that will give you 0 equals 3.
That logic makes sense too. I guess not, some of the terminology and some of the notation I'm not the biggest fan of, but what's going on makes sense most of the time.
No, it's
So,
not.
it's kind of a strange little world, I guess, for matrix.
It's another language,
Yeah,
and it's just a matter of just sort of learning a new language.
yeah, that makes sense.
It gets more, it gets easier and more comfortable over time.
Right. Yeah, like for example, some of the transformation notation, I really dove into the book over the weekend and stuff and realized that it really is, it's not that bad. If you can interpret what they're saying, it turns into pretty simple stuff most of the time. So
Yeah.
I've been realizing that over the last few days. So.
Basically, everything that we've done turns into row reduction.
Yeah, I noticed that too. So. All right, well, thank you very much.
Yeah.
So for the conversation about one-to-one and on-to, because it defines, one-to-one as if the columns are linearly independent, and on-to is it, for each B, for every B there's a solution. And it says that's the same as, it having a pivot in each row, so if there's a pivot in each row, it's onto, like, no matter what. And if there's a pivot in each column, it's one-to-one no matter what.
If they're linearly independent.
You have as many vectors in your basis for the range as you do pivots
Yeah.
in a non-augmented matrix. So if you have one in every row, that means it has the same dimension as your output. So your rows tell you what the dimension of the output is. So you have a span of a certain number of vectors equal to the dimension of your output, which
Mhm.
means they're the same dimension.
Okay.
So it's the whole space.
So
So,
the rows give you your dimension output.
Yeah.
You just period.
So-
Yeah.
Sentence.
They're always like, 1, 2, 3, 4, 5, 6. So all of your outputs will be linear combinations of these two. And they're three-dimensional. So all of your outputs have to be three-dimensional as well.
so if that question was like, for a 3x5 matrix, and we have three pivots, right off the bat, we could say it's onto, because we have three pivots.
Oh, and we have three
3 by
pivots.
5.
If we say that we have three pivots.
Yeah, so.
It's possible that we may have fewer than three pivots because we may have some of the rows completely wiped out during row reduction.
Yeah.
But you would have, I guess, you have two pivots here, so you, like, it's like, at least instantly, like, looking at it immediately, before you
Yeah.
reduce anything.
Yeah, we can tell these are linearly independent just by looking at them because one is not a multiple of the other.
No.
And so we will know instantly that we'll have these two as pivots. And so this will be one-to-one.
Yes.
So, my last detailed question on that class, when they're one-to-one, can two, you said this, I'm just trying to make sure I remember, I kind of forgot, can two inputs go into one output, is that allowed in one-to-one, or is that not allowed?
That's not allowed.
That's specifically what one-to-one disallows.
Okay,
So if that ever happens, that's what disqualifies it from being one-to-one. One-to-one means only one thing maps to that one thing. It's one-to-one instead of two-to-one or,
yeah, that makes sense, I guess I'm getting mixed up then, because you say onto, we'll have a, like a solution or a B for every, what do you call them? It seems like, I'm just getting mixed up in that a little bit.
for every AX equals B, you'll have a solution no matter what the B is, right?
No,
That's onto.
and one, two is, one is just, there's not anything really the same in place,
Yeah. Exactly.
unless I'm telling you wrong.
So this is the standard picture for functions,
Yeah,
right? So it's one-to-one if this never happens, and it's onto if this never happens, nothing mapping to this.
okay, so okay.
So this will be like 2-to-1.
So then and then like you were saying, if I drew 3 lines across horizontally, it's one-to-one and onto.
Exactly.
And Maybe that makes sense.
which means these things
Yeah,
are perfectly matched up. In vector spaces, that means they have to have the same dimension.
I see. And then if you had like the bottom two lines going across, and the top line went to the middle on the other side, then there's nothing. Because we're violating both definitions.
Yeah, so it's no longer onto,
Exactly.
it's no longer one-to-one. Now, if we just look at this,
Yeah, okay, yeah.
it would make it make sense again.
See what you're getting at, I think. Three going, the three space going to two.
Yeah.
That's on two.
This is now onto, but even though it's a smaller number, I could still change it again. If everything go to this, and suddenly it's not onto.
I mean, that makes a lot of sense. Yeah, I think the visuals like that are really helpful, I think. At least for me, I think that pretty well.
Yeah, the way you think about it is you take everything that can go into the input here, and you bring it all over. So if it's onto, it covers the whole space. It's right onto it, right? And if it's one-to-one, it means there's no overlap.
That makes sense. Okay. All right, thank you very much.
Yep.
So for the questions about finding what A is, the strict way to do that is just what do we call the elementary that here's right?
There's always more than one way to do these things. So, as long as we have, what am I trying to say? So if this is a transformation from Rn to Rm, if we are given U1 up to Un, independent vectors, then those independent vectors span Rn. And that means just based on these, we can figure it out. So if these are E1 up to En, so the standard basis vectors, then it's easy because the matrix is just TUB1, TUB2, right? So that in that case it's easy. In this case, we have to do a little more work.
I thought there was one like that on the web work, I couldn't remember.
So here's the key. Every single one of these is a linear combination of these.